So in this video, we're going to try to explain the concept of catalysts. So previously we talked about activation energy and that the activated complex occurs at the peak of the activation energy barrier. And this is energy that needs to be put in to break enough bonds to be able to make the reaction occur. The energy we put in to activate it, we get back, and then we have the enthalpy change, right? So our enthalpy change here is negative energy. But the catalysts are a chemical that are added to a reaction to speed it up. So when we did our esterification lab, we added acid catalyst, and the catalyst isn't used up. So we've got the acid at the end of it, but it reduces the activation energy. And so a typical catalyzed reaction will have a curve that'll go like this, and the enthalpy, the activation energy is much lower for the catalyzed reaction. So the reaction is easier to occur. It takes less energy to get started. We have the same amount of energy occurring, but the reaction speeds up because it takes less energy for the reaction to occur. Now this can happen because of a few different reasons. So reactions occur because of collision that happens with enough energy. This reduces the energy with the correct orientation. So one of the ways it can work is that the orientation is improved. And so perhaps it holds on to the two reactants so that they're in the right, facing the right direction. That sort of thing might happen with enzymes. Enzymes are natural catalysts that occur in biological systems, so your body has enzymes. And sometimes you'll have things like platinum will be a catalyst or some sort of metal surface that it reacts on. And if you provide the right kind of surface, it can make it so that the reactants find each other if they were gases, perhaps. But catalysts are speeding up the reaction by reducing the activation energy. The other way that this can occur, though, with a catalyst is by providing alternate reaction pathways. And so maybe there's one reaction and then a second reaction, and this has its own activation energy. You get some back and another activation energy. It's gone through multiple steps, but you have the same reactants and the same products, kind of like Hess's law. And because each of these has a lower activation energy for each of the reactions, they end up giving an easier pathway with a lower total activation energy than if you were just trying to do the direct reaction from the reactant to the product. Often, without a catalyst, many reactions are just exothermically or thermodynamically unlikely to happen. They just have, it requires way too much heat for it to occur naturally. So catalysts are a great way to speed up reactions. They do not affect the enthalpy of the reaction. The same reactants are made in the same products, and the catalyst is not used up. Right? So when we add a catalyst, it promotes the reaction. Now, one thing about catalysts are they promote the forward reaction, but you can also have the backwards reaction. So the forward reaction here is exothermic, but if we were to instead go backwards in this, the enthalpy we know would be positive energy, but the catalyst is still going to work going forward or backward. So the catalyst reduces the activation energy. Here, the activation energy for the forward reaction, uncatalyzed, is this. For the catalyzed reaction is this. Going in the reverse, the uncatalyzed reaction is this activation energy, and the uncatalyzed, or the catalyzed activation energy is this. So catalysts speed up the reaction by reducing the energy required to make the reaction occur. They are not used up.